right, great. So, all right, I'm going to try to go back to the beginning of this video. So this is a sequence of 3 short videos on YouTube. Each is about 5 or 6 minutes. Okay, they're entitled Doodling in Math, Spirals, Fibonacci, and Being a Plant. Okay, so if you wanted to look it up, this one has at least 3.5 or more million views. So I think I'm not the only one who watched it today. All right, let's try this. So let's see what happens. So listen carefully.
You're in your math class and your teacher's talking about, well, who knows what your teacher's talking about. Probably a good time to start doodling. And you're feeling spirally today, so yeah. Oh, and because of overcrowding in your school, your math class is taking place in greenhouse number 3, plants. Anyway, you've decided there's 3 basic types of spirals. There's the kind where as you spiral out, you keep the same distance, or you could start big but make it tighter and tighter as you go around and with piece of spiral ends. Or you could start tight but make the spiral bigger as you go out. The first...
Okay, so she speaks a little fast, and I think really slow. So I thought I might pause at some points in the video and discuss some of the things that she's talking about. Okay, so here she's saying that she's interested in drawing spirals. And oops, where did my chalk go? Oh, there it is. So she's saying to begin with, when you're drawing spirals, you could classify them into 3 different kinds if they're regular spirals. Okay, as you're drawing. Okay, this is a bad spiral. But you could keep the spacing between the different levels of the spiral equal. Like that. Okay, so that there's an equal spacing between them. Okay, another thing you could do is you could start a spiral and then let the levels get closer and closer together. All right, if you do that, then your spiral needs to end, otherwise it'll run into itself. Okay, but you could also have a spiral where the spiral starts close together and then gets farther and farther apart at each layer. Okay, and so in this case, as you do more spirals, the outline gets more and more circular. Okay, because if you have a large variation between the distance from the origin at different points here, that leads to only a small relative variation farther out. That's because all the points are farther out from the origin. Okay, and here she describes these as being good for making little slug cats. Meow. Okay, like that. Yeah, but as not necessarily useful for a lot of other applications. And this case is sort of interesting because it looks pretty and looks like some things that you might see in nature, maybe. And so we'll discuss those a little more. So sorry for that interruption, but I'm going to be interrupting several times because she talks a little fast for me. All right, thanks.
It's good if you really want to fill up a page with lines, or if you want to draw curved up snakes. You can start with a wonky shape to spiral around, but you've noticed that as you spiral out, it gets rounder and rounder. Probably something to do with how the ratio between 2 different ends of which each one is repeatedly and the same number 12, but you can bring the walk back by exaggerating the bumps, and it gets all optical illusion-y. Anyway, you're not sure what the second kind of spiral is good for, but I guess it's a good way to draw snuggled up slug cats, which are species you've invented just to keep this kind of spiral from feeling useless. This third spiral, however, is good for all sorts of things. You could draw a snail or a nautilus shell, an elephant with a curled up trunk, the horns of a sheep, a fern frond, a cochlea, and an inner ear diagram, an ear itself. Those other spirals can't help but be jealous of this clearly superior kind of spiral, but I've drawn more slug cats. Here's one way to draw a really perfect spiral. Start with one square and draw another next to it that is the same height. Make the next square fit next to both together, that is, each side is length 2. The next square has length 3. The entire outside shape will always be a rectangle. Keep spiraling around, adding bigger and bigger squares. This one has side length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and now 21. Once you do that, you can add a curve going through each square, arcing from one corner to the opposite corner. Resist the urge to zip quickly across the diagonal if you want a nice smooth spiral. Have you ever looked at the spirally pattern on a pine cone and thought, hey, sure are spirals on this pine cone?
Okay, so I just wanted to point out what we just saw there was that she's talking about a way that I could draw spirals like this in a very beautiful way, okay? And that is by using little squares on graph paper. And once you have 2 of them, to connect to a square with that side length. And then once you have a second one here, you can take this side length to be the side length of square, like that, and then this to be the side length of a square. Okay, and then you could connect the boundary points like that, and you see that this leads to a pretty spiral. I should also mention that the side lengths of these squares, 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 5, those are called the Fibonacci numbers. Okay, 1, 1, 2, 3, 5, and then there's a lot more. There was one that was 8, and then 13, and then 21 in her video there. Okay, and you notice that these rectangles, the ratios of their sides are different because their side lengths are different. Okay, this one has a ratio of, the big rectangle here has a ratio of, let's see, 5 plus 3 is a total side length of 8, and this has a total side length of 5. Okay, so that's a ratio of 2 Fibonacci numbers. But that's not too far from, let's see, okay, from something that's called the golden ratio, which we'll discuss a little later. Okay, all right. So.
Why there's pine cones in a greenhouse? Maybe the greenhouse is in a forest. Anyway, there's spirals, and there's not just one either. There's 1, 2, 3, 4, 5, 6, 7, 8 going this way. Or you could look at the spirals going the other way, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Look familiar? 8 and 13 are both numbers in the Fibonacci series. That's the one where you start by adding 1 and 1 to get 2, and 1 and 2 to get 3, 2 and 3 to get 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on. Some people think that instead of starting with 1 plus 1, you should start with 0 and 1. 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and it continues on the same way as starting with 1 and 1. Or I guess you could start with 1 plus 0, and that would work too. Or why not go back one more to negative 1, and so on. Anyway, if you're into the Fibonacci series, you probably have a bunch memorized. I mean, you've got it in 1, 1, 2, 3, 5. Finish off the single digits with 8 and 13, how spooky. And once you're memorizing double digits, you might as well know 21, 34, 55, 89, so that whenever someone turns a Fibonacci number, you can say, happy Fib birthday. And then, isn't it interesting that 144, 233, 377, but 610 breaks that pattern, so you better know that one too. And oh my goodness, 987 is a neat number, and well, you see how these things get out of hand. Anyway, 'tis the season for decorative scented pine cones, and if you're putting glitter glue spirals on your pine cones during math class, you might notice that the number of spirals are 5 and 8, or 3 and 5, or 3 and 5 again, 5 and 8. This one was 8 and 13, and one Fibonacci pine cone is one thing, but all of them? What is up with that? This pine cone has this funky weird part. Maybe that messes it up. Let's count the top. 5 and 8. Now let's check out the bottom. 8 and 13. If you wanted to draw a mathematically realistic pine cone, you might start by drawing 5 spirals one way and 8 going the other. I'm going to mark out starting and ending points for my spirals first as a guide, and then draw the arms, 8 one way and 5 the other. Now I can fill in the little pine cone things. So there's Fibonacci numbers in pine cones, but are there Fibonacci numbers in other things that start with pine? Let's count the spirals on this thing. 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So these are hard to keep track of, but they're in spirals too. Fibonacci numbers. What if we look at these really tight spirals going from this way up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Can we find a third spiral on this one? Sure, put them like this. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. But that's only a couple of examples. How about this thing I found on the side of the road? I don't know what it is. Probably social pine cone. 5 and 8. Let's see how far the conspiracy goes. What else does spiral say? This artichoke is 5 and 8. So does this artichoke looking flower thing. And this cactus fruit does too. There's an orange cauliflower with 5 and 8, and a green one with 5 and 8. I mean, 5 and 8 up is actually 5 and 8. Maybe plants just like these numbers though. Doesn't mean it has anything to do with Fibonacci, does it? So let's look at some higher numbers. We're going to use some flowers. I think this is a flower. It's got 13 and 21. These daisies are hard to count. They have 21 and 34. Now let's bring in the big guns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 42, 43, 54, 55. I promise this is a random flower and I didn't pick it up specially to trick you into thinking there's Fibonacci numbers and things, but you should really count for yourself next time you see something spiraling. There's even Fibonacci numbers in how the leaves are arranged on this stalk, or this one, or the Brussels sprouts on this stalk are beautiful, delicious green vine. Fibonacci is even the arrangement of the petals on these lilies, and some flowers have shown Fibonacci numbers as high as 144. It seems pretty cosmic and wondrous, but the cool thing about the Fibonacci series and spiral is not that it's this big, complicated, mystical, magical Superman thing beyond the comprehension of our puny human minds that shows up mysteriously everywhere. You'll find that these numbers aren't weird at all. In fact, it would be weird if they weren't there. The cool thing about it is that these incredibly intricate patterns can result from utterly simple beginnings.
Okay, so that's the end of the first of the 3 videos. So I hope it was clear what she was talking about, but in case it wasn't entirely clear, if you look at something like the bottom of a pine cone, you see different things going outward from the center, shapes formed by the plant, and your eyes can kind of see spirals there. Like, you tend to see spirals that go outward. They're kind of partly sort of a creation of your mind, but there really are kind of patterns to them. And if you look at the number of spirals that go, say, leftward, starting with the ones that touch the center, you tend to see the number of spirals as being a Fibonacci number. Okay, now there's obviously going to be a few mutant exceptions out there, but in general, we tend to see Fibonacci numbers. And if you add kind of more sophisticated spirals, like, say you're looking at petals that are farther apart, like that, you can still see kind of spiral shapes, but if they're very narrow and spaced very far apart, there's going to be more total spirals around than if you just look at the fat ones in the middle. Okay? And so when you count those, you tend to also get Fibonacci numbers. As long as you look at the spacings in an even way, you tend to see Fibonacci numbers. Now, I'm not guaranteeing that, but I'm saying it's very likely to happen. And that's the observation that Vihart is making in this part of the video. So you often see 8, 13, 13, 21, 5, and 8, depending on how you choose, say, a pair of spirals emanating from the center. Okay, and in the next video, she starts to talk about observations and why we might be seeing Fibonacci numbers over and over and over again in all these different things. So not just pine cones, but pineapples. And when you have, a sunflower, you have all these little dots here, but they also form spirals out from the center. Okay, so I'm going to move on to the second video. If you all have any questions at any time, you can just raise your hand, and I'll see if I can answer it or not. I don't know everything about this, but I can try to answer any questions you have. Okay, let's see part 2.
Say you're me and you're in math class and you do those flowery petally things. If you want something with lots of overlapping petals, you're probably following a loose sort of rule that goes something like this. Add new petals where there's gaps between old petals. You can try doing this precisely. Start with some number of petals, say 5, then add another layer in between. But the next layer you have to add 10, and the next has 20. The inconvenient part of this is that you have to finish a layer before everything is even. Ideally, you'd have a rule that just lets you add petals until you get bored. Now imagine you're a plant, and you want to grow in a way that spreads out your leaves to catch the most possible sunlight. Unfortunately, and I hope I'm not presuming too much in thinking that, as a plant, you're not very smart. You don't know how to add numbers to create a series, you don't know geometry and proportions, and can't draw spirals or rectangles or snowcats. But maybe you could follow one simple rule. Botanists have noticed that plants seem to be fairly consistent when it comes to the angle between one leaf and the next. So let's see what you can do with that. So you grow your first leaf, and if you didn't change angle at all, then the next leaf you grow would be directly above it. So that's no good because it blocks all the light or something. You could go 180 degrees to have the next leaf directly opposite, which seems ideal. Only once you go 180 again, the third leaf is right into the first. In fact, any fraction of a circle with a whole number as a base is going to have complete overlap after that number of terms. And unlike when you're doodling, as a plant, you're not smart enough to see you've gone all the way around and now should switch to adding things in between. If you try and postpone the overlap by making the fraction really small, you just get a ton of overlap in the beginning and waste all this space, which is completely disastrous. Or maybe other fractions are good, the kind that position leaves in a star-like pattern. It will be a while before it overlaps, and the leaves will be more evenly spaced in the meantime. But what if there were a fraction that never completely overlapped? For any rational fraction, eventually the star will close. But what if you used an irrational number, the kind of number that can't be expressed as a whole number ratio? What if you used the most irrational number? If you think it sounds weird to say one irrational number is more irrational than another, well, you might want to become a number theorist if you're a number theorist. You might tell us that phi is the most irrational number, or you might say that's like saying of all the integers, 1 is the integeriest. Or you might disagree completely, but anyway, fine. It's more than 1, but less than 2. More than 3 over 2, less than 5 over 3. Greater than 8 over 5, but 13 over 8 is too big. 21 over 13 is just a little too small, and 34 over 21 is even closer but too big, and so on. Each pair of adjacent Fibonacci numbers.
I'm not sure if you're still getting everything. She's kind of going pretty fast. So there's a lot that's going on here. Okay. First, she's talked about if you're a plant and you want to grow your leaves so that they all get a fair amount of sunlight. Okay, how should your leaves be positioned relative to each other? The angles they make if you look down on the plant from above. Okay, and then she's suggesting that somehow irrational numbers should play a role in how the leaves are spaced. Okay, and then she's jumping to exactly how big is this particular irrational number phi. So I think this is a good place to take a quick pause and talk about a little bit of the mathematics in a slower pace. So over here, I'm going to erase this. Okay, so I know you just saw this, but because I'm so slow, if you have a leaf and then higher up you put a leaf at the same position, then the sunlight can't reach the second leaf. And this makes the second leaf really sad. And so what you do is, if you were a plant and you somehow knew where your leaves were going to go, you would put this leaf somewhere else that didn't block the light. So you could put it the farthest away, which would be over here. And that works great for these two leaves. But then if you're a plant, once you start growing leaves, you have to kind of complete the pattern because you're not as smart as a mathematician. And so if you continue the pattern like that, then the light will come and hit these two, but not hit that one. And so you see that if you rotate the leaves in any regular way, with any angle between the leaves equal to 360 degrees over, say, 5, or 360 degrees over, say, 6, then after you've grown 5 or 6 leaves as a plant, eventually you get a leaf that's directly on top of the leaf that you started with, and then that bottom leaf is not getting sunlight. And so the idea is that maybe plants have angles between their leaves that is 360 degrees divided by some irrational number. Because at least then there wouldn't be a perfect overlap completely blocking the light to one of the leaves. Because if you kept rotating by the same angle, you'd never completely block the light from a leaf below it, because it doesn't complete a full circle after a set finite number of steps. But I'm not sure Vihart presents convincing evidence that it has to be phi from the beginning. I think she's sort of saying, well, phi is irrational, and we should study it, and later we find out that it's the right answer. But I don't think, she doesn't logically deduce that this number should be phi. Okay, that's kind of more experimentally observed. Okay, something that we can't fully explain at this stage. Okay, but is something that is widely observed and happens to be the physically correct answer, even if we can't completely explain it with just what's on the board. Okay, so second, she says phi is the most irrational number. And that statement is not entirely precise. So there's different meanings that you could assign to the phrase most irrational. And one thing that you could say is that, well, what does it mean to be irrational? It means that you're not rational. Okay? So if you're thinking you can measure how irrational something is, oh, no. Okay. All right. Well, I have some time before I need it again. The most, well, okay, rational means fraction. So somehow the most irrational, if you're trying to understand that concept, would be something that's the least fraction-like, somehow, if you could measure that. All right? So if you think of a number like the square root of 2, you can write its decimal out, and that's telling you something about how close certain fractions are to this irrational number. You know that 1.4 is less than root 2, and root 2 is less than 1.5. So, in other words, 14/10 is less than root 2, and root 2 is less than 15/10. Okay? So somehow, each of these fractions is less than a distance of 1/10 from the square root of 2. Okay? And so you could say that these fractions are closely approximating the square root of 2. But their error would be this part. So 14/10 is close to root 2, but it's off by 0.014, blah, blah, blah. Okay, because it's not exactly equal to 14/10, it's an irrational number. So then you could start to measure the distances between irrational numbers and fractions with small denominators. And so you could say, for example, among all the fractions that have a denominator from 1 to 10, okay, which one has the smallest distance to my thing, to my irrational number? And so this one might have the smallest distance among the ones with a denominator 1 through 10 to the square root of 2. But somehow, there's a sense which is a little complicated to define, in which, given a certain denominator, say 5, the closest number with a denominator of 5 to the Fibonacci number, I'm sorry, the golden ratio, is this one. This one is the closest. Okay? You can just check all the things with a denominator of 5, 4, 3, 2, or 1, and 8/5 is the closest. But it's not that close. Okay? The error here, the distance between these, is still not that small. It's not like 400ths, okay, or 4,000ths. It's significantly bigger than that. And so somehow there's a sense in which, but it's very hard to define exactly, that the closest rational number with a small denominator to phi at each stage, okay, denominator 5, denominator 8, denominator 13, and so on, is still almost as far away as it could be and still be the closest rational number with that denominator. Okay? And once you make this concept precise, you can prove, although it's very difficult to prove, that a number has that bad approximation property if and only if it looks like this, with AD minus BC equal to plus or minus 1, and A, B, C, D whole numbers. Okay? So all of these numbers are hard to approximate, like phi. Okay? But phi is the simplest number that is very hard to approximate. Okay? That does not give you any evidence that phi should be the thing that relates to the turning of leaves in plants. But it sort of gives you some idea of what Vihart might mean by saying that phi is the most irrational. Okay? There's a way to make that precise, although it's a little complicated. All right? So the second thing is she starts talking about the relation between these fractions. Is this going to work? Okay.
Computer just keeps sleeping.
Okay. All right. Okay.
Yeah.
So the second thing is that phi seems to be related to the ratios of Fibonacci numbers. Phi is greater than 1. Phi is less than 2, which is a ratio of 2 Fibonacci numbers. Phi is greater than 3/2. Phi is less than 5/3, and so on, which is very interesting. So the odd things on this list get smaller. 1 is bigger than 3/2. So this is getting smaller. And then the even entries of my list, they're getting big. They're getting, let's see, wait. No, this is getting bigger. Okay, bigger. And these get smaller. 2/1, then 5/3. So these are getting smaller. And somehow the number phi is being trapped in between these two, the even entries on my list and the odd entries on my list. One is getting smaller, the other is getting bigger, and phi is somehow trapped in between. And those are ratios of Fibonacci numbers. Okay? But one thing I think V. Hart probably should do that wasn't done is she doesn't say what the golden ratio is. She doesn't define it mathematically. She just said it has these properties. And I think it would be fun to actually like say, oh, this is what the golden ratio is. So I want to do that really quick. So I'm going to erase this. So the Greeks saw the golden ratio as, let me see. As a ratio between sides of a rectangle. Okay, so I could make this side length 1, then the ratio would be the same as this side length. Okay, so the ratio of the two side lengths is now x to 1. All right, and then that rectangle is considered a golden rectangle by the Greeks if when you put a square here whose side length matches this side length, so like this, okay, then the ratio of the long side of this new rectangle to the short side is the same as the ratio of the long side of the old rectangle to the short side of the old rectangle. Then we say that it's a golden rectangle, and the ratio between the sides is called the golden ratio. So let's calculate what these side lengths are. This has a side length of x, and this is supposed to be a square here, so this should have a side length of x. But then this has a side length of 1. So I'd add the two together. And so the ratio of these two side lengths is the long one divided by the big one. I'm sorry, the long one divided by the short one, I meant. So that's 1 plus x divided by x. And so x, which is positive, is equal to the golden ratio if the two ratios for the small rectangle and the big rectangle are equal to each other. Okay? That's where the golden ratio comes from in Greek mathematics. But how do I know that the golden ratio is bigger than 1 and less than 2 and bigger than 3/2 and less than 5/3 and all of those things? Well, I can take this equation and I can solve for x. Then I'll know exactly what the golden ratio is. And then I can certainly calculate it and see if it's bigger than 1, smaller than 2, and all those things. Okay? So that's what was actually done. The Greeks didn't study Fibonacci numbers, really, as far as I know. Okay? So they had to do things, you know, using the Babylonian ability to take square roots and things like that. So let's solve this for x. We can multiply both sides by x and 1. We get x squared equals 1 plus x. This becomes x squared minus x minus 1 equals 0. I hope I'm not moving too fast for you. But we get a quadratic equation after we multiplied by x. And there's a formula for the solution to quadratic equations. And it says that x equals negative b plus minus the square root of b squared minus 4ac all over 2a. And so we get 1 plus or minus the square root of 5 over 2. Okay? Now, if we choose the minus sign, it won't be positive. It will be a negative number. Because if you take 1 and subtract the square root of 5, you get a negative number. So the one that's greater than 0 is the one with the plus sign. And so phi is 1 plus the square root of 5 over 2. And that's the golden ratio. And then if you want to know, okay, how does it compare with some of these fractions of Fibonacci numbers, you could work by hand or get out a calculator and calculate the first few decimal places of this. Okay, and you see it's approximately 1.6. Okay, a little bigger than that, or smaller or something. Anyway, it's approximately 1.6. Okay, so then once you know that, you can say, oh, it's bigger than 1, less than 2, bigger than 3/2, and less than 5/3. So that's some background about the golden ratio. And if you think about how those rectangles were constructed, whose side lengths were Fibonacci numbers, you can see that at each stage, you get something. Well, I've drawn it very badly. But if you look at this one, it sort of looks like you're constructing something that's almost a golden rectangle. Okay? At each stage, you get something that's almost a golden rectangle. And so that may provide you some hint that maybe the Fibonacci numbers do make good approximations to the golden ratio, the ratios of the Fibonacci numbers, because they're somehow close here. All right. So let's see. I sort of think this is a fun topic. So I'd actually like to show a bit more about the connection between the Fibonacci numbers and the golden ratio here. Maybe I won't provide full proofs, but maybe some slightly more mathematical discussion. So what is the formula, or how are the Fibonacci numbers related to each other? Okay, when I construct this square, it has side length 2. I got it by adding the side lengths of the 2 previous squares. And this one with a side length of 3, I got it by adding the side length of this square and then this square before that. And this square that has a side length of 5, I got it by adding the side length of this square, 3, plus the side length of this square, 2. So we end up with equations like this, generating the Fibonacci numbers. So at each stage, excuse me, at each stage, we see that the new Fibonacci number is equal to the previous Fibonacci number plus the Fibonacci number before that. Okay, so if we start with a couple of Fibonacci numbers, then the next one will be the sum of the previous 2. And then the next one will be the sum of the previous 2. And so on. Okay, so if we want to say something about the ratio of a Fibonacci number to its predecessor, we take this equation, which creates the Fibonacci numbers, and just divide both sides by the Fibonacci number before this one. And what do we get? We get this ratio equal to this ratio. So we're saying that this ratio equals 1 plus Fn minus 1 over Fn. Okay, I just got this by dividing both sides by the nth Fibonacci number. These sort of look weird. This one decreases, this one increases, but we can write it like this. One over the fraction Fn over Fn minus 1. Okay? So I just took this fraction and I multiplied the top and bottom by 1 over Fn minus 1. So when I did that, the top became 1 and the bottom became this. Now, if you're looking at ratios of Fibonacci numbers, this is the ratio and this is the ratio before it. Okay? And we can check all this stuff, right? Like 5/3, is it equal to 1 plus 1 over 3/2? Okay? Because that's what this says if I take n equal to whatever one corresponds to 5 there, right? Are the things I'm writing down true, or did I just make mistakes? Okay? Well, I can check it. 1 over 3 halves is the same as 2/3. 1 plus 2/3 is really equal to 5/3. So I'm not just writing false equations. This is not nonsense. Okay? On the other hand, what was the equation that defined the golden ratio? Okay? It was the equation x equals x plus 1 over x. Okay? It also is a fraction on the right side. But x divided by x is 1. So this is the equation x equals 1 plus 1 over x. Okay? This was the equation for phi. This equation, x equals 1 plus 1 over x, is a little bit like this equation, where the fraction equals 1 plus 1 over the preceding fraction. Okay? So there is some mathematical similarity here. So if these fractions get closer and closer together, okay, and if they're going closer and closer to a particular number, which I would call x, then we would have the following. If all the fractions, okay, as n gets bigger and bigger, okay, as n gets big, get closer to a number x, then x should, so I'm not giving a rigorous, geometric or numerical proof. I'm just saying you might believe something like this. Okay? X should satisfy the equation x, because this one is going to be close to x, because we're picking x as the number they're getting close to. Okay? This one's close to x. 1 plus 1 over x. Right? Because if this is close to x, then this right side is going to be close to 1 plus 1 over x. If this is close to x, then the left side is going to be close to x. And you could imagine that maybe the limit is going to match both sides. Because both sides were equal at the beginning, maybe they'll be equal at the end. All right? But then x will equal the golden ratio phi, because phi is the only positive number that satisfies that equation. We found that out we found all the solutions to that equation with the quadratic formula. And we know there's only one positive solution. So this is saying that assuming that these fractions, as n gets big, get closer to a number x, and x is a reasonable number, then the ratio of the Fibonacci numbers is getting closer and closer to the golden ratio phi as n becomes large. And this is the deep connection, or one of the deep connections, I should say, between the Fibonacci numbers and the golden ratio phi. All right? How much time do I have? I might want to say a little more about this. Yeah, we have 20 minutes and less than 8 minutes of video. So let me mention one other cool thing, all right? And that is that mathematicians in the 1500s and 1600s, they started to develop ways of understanding fractions that didn't involve geometry and didn't involve decimals, okay? That involved simpler fractions, okay? So suppose I have an example like, say you give me an improper fraction, like think of something that's ugly but not too complicated, like 23 over 19, okay? That's a fraction, it's a little ugly, not pretty like 1/3 or 1/4, but it's a little complicated, okay? Then there's a way to write it in a way that I find complicated, but mathematicians at that time thought was pretty. And that is as follows. They said, given a fraction like 23 over 19, write it as a whole number plus a proper fraction. Then said, that part's pretty, this part is still not pretty enough for them. Okay? They like fractions that have a numerator of 1. They don't like any other fractions. That's how they define pretty. Okay? I may not agree because I'm very modern in my tastes, but that was their viewpoint. So you could try to force this fraction to have a numerator of 1. You would run into trouble. Okay? So you would do this. Okay? I made its numerator 1 by dividing the top and bottom by 4, but now the bottom is not a whole number. That's bad. But you could think of this fraction as being kind of like this fraction. It's an improper fraction equal to a whole number plus a proper fraction. So 19 over 4 is going to be 4 plus 3/4. Okay? You see how I don't like this? Because it's getting more complicated. Okay? But people who did this thought it was very pretty. So they can have it. But I'm going to finish this process here. I can make this have a numerator of 1 by dividing the top and bottom by 3. And I end up with this. Okay? You see how I don't like it? You see how it's getting more fraction-y? Yes. But anyway, if you're persistent, you can continue. 4/3 is 1 plus 1/3. This is called the continued fraction expansion of the number 23 over 19. Okay? You see how no numerators are anything but 1. Every numerator you see is a 1. Numerator of 1, numerator of 1, numerator of 1. And people who did this thought it was very pretty. And one advantage of this, number theoretically, not practically, is that the continued fraction expansion has to do with the number itself and not with how we represent numbers. Okay? Think of a decimal expansion like 3.141. Why is it base 10? Because we have 10 fingers or something like that. Okay? But if we had alien relatives on a distant planet, farther out than Mars, because we found out we don't see a lot of people walking around on Mars, they might have 8 fingers, and they might use base 8. Okay? Or they could have 12 fingers and use base 12. So our numbers might look different from theirs. Okay? But our continued fraction expansions would be pretty similar. Okay? We might have different symbols for the number 4 and the number 3 and the number 1. Okay? But we'll still have the same continued fraction expansion provided you swap the symbols for 4 and 3 and 1 to our symbols. Okay? So somehow this has an intrinsic meaning related to our number that's useful maybe for number theoretic research. Okay? Now what does this have to do with the Fibonacci numbers and the golden ratio and plants and all of that stuff? Well, remember, the golden ratio satisfies this equation. This equation. But anytime I see x, I could substitute 1 plus 1 over x. I could do it, because they're the same thing. So what happens if I take this x and I replace it with x equals 1 plus 1 over x? Okay, so I had x here, but now I'm replacing it with this thing. I get 1 plus 1 over x. Okay, because this and this, they're the same by our first equation. Really tricky. This looks like a continued fraction expansion. Okay, so I could do it again. I could replace x with 1 plus 1 over x. I would get this. Okay, you could keep doing that if you wanted to. And you could hope that the fractions you get are going closer and closer to some number. Well, okay, all the numbers are equal to x. So they're all just x. And you could end up saying that phi is equal to 1 plus 1 over 1 plus 1 over 1 plus 1 over, kind of going forever. Okay? I haven't defined rigorously what that means, but you can believe that once you do define precisely what it means, you could prove such a thing. Okay? And the numbers you get by removing one of the fractions at one of the stages, those are the best rational number approximations to your number in a suitable sense. And the fact that there are only ones here is how mathematicians prove that the golden ratio phi is the most irrational. It's part of their proof. Okay? I'm not showing you the details because they're complicated, but it's part of the proof. Somehow you can never have a number like 2, and as soon as your fraction is a 2, you get really close to it. Okay? Because you go by 2 instead of by 1. Okay? But the proof is complicated. But what if you do look at these approximations generated by the continued fraction expansion? Okay? What are those approximations? You get, oops, I should have a 1 plus at the beginning. Sorry about that. We get 1, and then 1 plus 1 over 1 is 2 over 1. And then 1 plus 1 over 1 plus 1 over 1, that equals 1 plus 1 over 2 equals 3 halves. And 1 plus 1 over 1 plus 1 over 1 plus 1 over 1, that equals 1 plus 1 over 1 plus 1 half. That equals 1 plus 1 over 3 halves. That equals 1 plus 2/3 equals 5/3. You see what these numbers are, don't you? They're those ratios of Fibonacci numbers that we were using before. So the approximate continued fraction expansions of the golden ratio phi are always the ratios of two neighboring Fibonacci numbers. And so the connection between Fibonacci numbers and the golden ratio is much deeper than just saying that, oh, the limit of the ratios of the Fibonacci numbers is phi. Okay? I can take the decimal expansion of phi, and that's also a sequence of rational numbers that gets close to phi. It's decimal expansion, which has nothing to do with the Fibonacci numbers. Okay? But this shows that somehow the ratio of the Fibonacci numbers are intimately connected with the number theoretic nature of the golden ratio in a very deep way, deeper than decimal expansions. So I really wanted to share that with you all today. Okay, we can finish this video. I think I've talked for a while about that. Okay. Anyway, I thought that was cool.
Do you want me to just play it?
Yes, if you can. We don't see a video up here. At least I don't see.
You fall asleep.
Uh-oh. Well, I don't know. I thought, okay. All right.
I read it a little bit, so I'm just going to rewind.
Okay.
Each pair of adjacent Fibonacci numbers creates a ratio that gets closer and closer to phi as the numbers increase. Those are the same numbers on the sides of these squares. Now stop being a number theorist and start being a plant again. You put your first leaf somewhere and the second leaf at an angle which is 1/5th of a circle, which, depending on whether you're going one way or the other, could be about 222.5 degrees or about 137.5. Great. Your second leaf is pretty far from the first, gets lots of space in the sun, and now let's add the next one 1/5 of a circle away, and again, and again. You can see how new leaves tend to pop up in the spaces left between old leaves, but it never quite fills things evenly, so there's always room for one more leaf without having to do a whole new layer. It's very practical, and as a plant, you probably like this. It would also be a good way to give lots of room to seed pods and petals and stuff. As a plant that follows this scheme, you'd be at an advantage. Where do spirals come in? Let's do a little pinecone using this same method. By the way, you can make your own phi angulotron by dog-earing a corner of your notebook. If you folded it so the edge is on the line, you have 45 degrees plus 90, which is 135, pretty close to 137.5. If you're careful, you can slip in a couple more degrees, detach your angulotron, and you're good to go. Add each new pinecone thing a phi angle around, and make them a little farther out each time. which you can keep track of by marking the distance on your angulotron. Check it out! The spirals form by themselves, and if we count the number of arms, look, it's 5 and 6. If you're wondering why spirals were formed and why only with 5 and not 2 numbers, you could morph back into number theory for diameter or something. But here's just a little bit of intuition. One simple way to do a flower is to start with a certain number of petals, say 5, and when you go back around, add the next layer close to the first but bigger. Each layer adds 5 new petals, and the 5 arms spiral out. Looks pretty spirally to me. Now go back to 5. You put out 3 petals before you go back around, and if I make them really wide, the next lap adds 3 petals that overlap a bunch with the first, and so on. If I started with skinnier petals, though, the second time you go around it doesn't quite overlap so much, and it takes 8 petals before it goes around twice and they overlap enough for you to see the spirals. So this time I get 8 and 13. I mean, none of the spirals are actually physically there on any of these plants, it's just the plant bits are close enough that you can see the pattern. So all a plant needs to do to get awesome Fibonacci numbers of spirals is add new bits at 137.5 degree angles. The rest takes care of itself. That the Fibonacci series is in so many things really says less about those things and more about mathematics. I mean, that's what mathematics is all about. Simple rules, complex consequences. A process so easy that even a plant can do it, can turn into these amazing structures all around us. Just like a few simple postulates can give us an incredibly powerful geometry. I mean, that's all assuming that a plant can do it. But measuring the angles between plant bits, you can see they obviously do it somehow. I mean, it's not like they have anglotrons, but plants have been around a long time and have had a lot of practice, so that probably explains everything. And thus, we always get spirals of 5 and 8 on this flower, 5 and 8 on this artichoke, 5 and 8 on this pine cone. Even this cauliflower has 1, 2, 3, 4, 5, 6, 7. Anyway, we always get 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4. It's easy to dismiss these as mutant anomalies, but just because they're different and unusual doesn't mean we should ignore them. 4, 7, 11? What could these numbers mean? Maybe things aren't as simple as I thought.
Okay, I think we don't have enough time for the third video, but you're welcome to watch it on your own in your own time. I think they're all fun. I do want to mention something from the third video about why it might be that we so often, but not always, see the golden ratio in the angle between the leaves. Okay, because that's the real biological mystery that drives a lot of these videos. And you can think of the stem of the plant as having in it a kind of growth hormone by which it produces and grows leaves. Okay? So if you have this growth hormone coming up and suddenly you have one leaf, okay, then the growth hormone, you could think of it as consisting of droplets. And each droplet has a very tiny amount of electrical charge in it. Okay, very small, but each one has a little bit. Okay, that's the way I'm thinking about it. Well, then this leaf might have a slightly different electrical charge than these droplets. And so different charges, like positive and negative, no, let's see. But it's going to be a different charge, but it'll still be the same sign. Like they'll both be positively charged or both be negatively charged. That kind of thing. Okay? And again, I'm not being very scientific or detailed here. All right? But just giving you some idea. Then this one will repel these a little bit because they're the same charge. Like charges repel. And so this droplet, these droplets will tend to form on the opposite side here. And so your next leaf, as it's growing, will be growing kind of on the opposite side of that one. Okay? So that's why in plants where the leaves are very spaced apart, you actually do get leaves on opposite sides. If they're really far apart, okay, then they do block some sunlight. So they're sort of stupid plants, but they do exist, okay? Evolution didn't kill them all right? But then if you're going to grow another leaf, okay, then you want droplets that form that are far away from both of these two leaves you already have. Well, what's going to happen is that the plant's going to pick one side, okay, because at the beginning the two leaves are equally spaced, okay? But there's going to be some imperfection in the plant, and it'll pick one side, okay? So then there'll be a lot of droplets on one side, and this plant, and this leaf, as it grows, moves a little bit over here as it follows up the stem, and then there'll be a leaf here. Okay? But it won't be exactly even because this leaf, because it grew first, is bigger. Okay? This leaf, because it grew second, is not yet full size. And so this third one, it's not going to be equal 120-degree angles over here. Okay? Instead, the angle with the smaller leaf will be a little smaller than 120 degrees, and the angle with the bigger leaf will be a bit bigger than 120 degrees. So it'll be about, according to physical law, it would be approximately 127.5 degrees. Okay? But then if you measure this complementary part, 360 minus 127.5, you get to, let's see, well, anyway, I think you get approximately 360 degrees over phi. Okay? It's never actually equal to this because, I mean, well, I guess it could be, but it's probably never exactly equal. But as you get more and more leaves, it probably gets closer and closer to this based on how things go. All right? But if you have a mutant plant that starts by growing 2 baby leaves at the same time, okay, then because these are the same age and size, you won't get angles exactly like this. And you'll get slightly different angles and slightly different numbers of spirals, and that generates a lot of the different examples where you don't have Fibonacci numbers in the plants. But the same underlying mechanism is present in both. And so you can get Fibonacci-like sequences that are not exactly the same as the Fibonacci numbers that will predict the number of spirals on those other plants. Okay, well, that's my talk for today. Thank you very much for coming. If you have any questions, I'd be happy to answer them. Otherwise, have a fantastic day.